In this video, we're going to have a look at how to handle the families of function style questions in the context of the hyperbola, the truncus, and the square root. Enjoy. Cool. So the agenda of today is to simply finish up the chapter 4 style stuff when it has the miscellaneous types of functions. So we're talking about like hyperbola, truncus, square root, and we're specifically looking at the families of functions style questions when it comes to those particular graphs. What that means is you're simply given a generic equation for whatever type of function is being asked about, and you have to solve one or more unknowns for that function. Now, the way you do that is with whatever key information is given for that question. In the case of a hyperbola, if we see in this example on the screen share, we have a fully generic hyperbola. It's got an a, h, and a plus c, and we're told some key information about it. So we have a vertical asymptote, x equals 3, horizontal asymptote, y equals 1, and we're told the hyperbola passes through a particular point. So you'll notice there's 3 individual pieces of information for 3 individual unknowns. Our goal is to simply translate the written version of that information into a particular variable. So for example, our vertical asymptote, does anyone know, I know it's on the page, does anyone know what's responsible for setting the vertical asymptote of the hyperbola?
Is it h
Yeah.
in the x translation?
Precisely. So whatever's in this denominator here with a minus h, if it's a vertical asymptote at x equals 3, we're going to get h equals 3. So that'd be x minus 3 in that case. For the horizontal asymptote, again, it's written, but who wants to jump in and tell me? What's that going to be set by?
C.
Yeah, C, precisely. Whatever this is, whatever the plus something is at the end, that's your vertical translation, and so that's going to set your horizontal asymptote. Now, in every circumstance, it doesn't matter what function you have, it could be hyperbola, truncus, square root, it could even be like polynomials all the way back into that, logarithms, exponentials, all that is going to have some dilation factor A, and I've yet to see a case where A was not solved by subbing in another known point. So the vast majority of the time, you sub in the point after you've solved all the other unknowns, and you can just quite quickly rearrange for A under those circumstances. Hyperbola is usually nice and easy because when you do your rearranging, it becomes basically just a linear equation. But okay, that is that. Next up, truncus. Very similar. In fact, it could be identical to how you handle the hyperbola, because truncus also has vertical and horizontal asymptotes, and those are determined by the exact same terms. So to make it a little bit different, I've only given you the vertical asymptote, and I've given you 2 additional points. Now, the information that you're given will depend from question to question. You're not guaranteed to get like asymptote information or just point information. We're just going through a few different examples of what could be presented. So in this case, again, vertical asymptote is going to be your horizontal translation. That gives you a nice and easy h equals 1. Then from there, you've got these 2 unknown, or these 2 additional points and 2 unknowns to solve. When you have that, it usually implies you're going to have to be doing some form of simultaneous equation to solve that. So first up, we're subbing in the point 2, 7, rearranging and simplifying. And the next one, -1, 19 on 4, again, simplifying down. You've got equation 1 here, equation 2 here. Both are linear, and so you can use whatever linear methods you like, whether it be elimination method, whether it be substitution method, is perfectly up to you. In this case, I've done elimination method, so I've done this equation minus this equation to cancel out the k. And then, yeah, rearrange for A, sub back in to solve for k. If anyone has any questions, feel free to hop off mute or pop something in the chat. But that's the gist of how you handle that one. For a square root, you tend to get a bit of different information regarding that. Typically, you get stuff to do with like range and domain and stuff like that. This is because your square root it has a vertex rather than like an asymptote to work with. And so part of the information they give is around where you start from your vertex and do you go up, down, left, right, that sort of thing. So in this case, we have range, maximal domain, and passes through a particular point. So a couple of things going on there. The range of your square root is always going to be determined by this k term and the sign of this a value. If it's positive, it should shoot up. If it's negative, it should shoot down. So the range of a half is going to mean, no matter what, our k is going to be a half. But the infinity side of things tells us that a is going to be positive. That's not super necessary to solve this. It's just nice to know that your a value should be positive when you finally solve it. Okay, so that's k. Next up, maximal domain. Now, I haven't gotten into a whole lot of detail here. Why does maximal domain of this imply h equals 1?
Because there's still like the x value given, and since h determines the x value of the asymptote, that's why you can sort of conclude from the maximum domain that it will be h equal 1.
Yeah, it's pretty good. Yeah, this horizontal translation will do the horizontal value of the starting point. And so if you think about horizontal as your x, then yeah, this starting point of x equals 1 should mean x minus 1 as your value in there. To add a bit more of a nuance onto that, the reason why there even would be a maximal domain of 1 to infinity here is because you want whatever's inside of your square root to be always positive or 0. Otherwise, you're taking the square root of a negative number, not a great idea. So if this is maximized, then when I have x equals 1, the root should go to 0. That's potentially another way of thinking about it if you don't like the maximal domain approach. But okay, we got our h, we got our k. Sure enough, we have a point, and we're solving for a. Same method as before, and sure enough, a does turn out to be positive, which we kind of assumed from before, based on the range shooting off to infinity rather than negative infinity. So that's more of like an error checking thing. Like if you get to here and you do get a negative, but this range implies a positive, you've now got a mismatch of information. You should probably consider either your solution for this or your solution for this. One of those has an issue. That's the gist of it, really. So all families of function style questions are going to look something like this. They're going to have some generic function. They're going to give you some information, and it's your goal to match up the information with the particular with the particularities of that function. Shall I clarify anything before we go into some questions? Okay. So we're just going to go top to bottom mostly. I'll pick out some key ones just so we don't have to like double up on repeats. But for the most part, we'll just go from the top. I'll pose a question to you guys, and we'll take it from there. Cool. So nice and easy. We'll start off with question 1. In fact, I'll do a screen grab of like all of this. Put it in the chat if you guys want to have a look at it from there instead, because we will be going back and forth between the handwritten notes if we need to. But yeah, starting with question 1, there's only one unknown in there, 1 point, solve for A. Any ideas how we might do that? Sub in the coordinate. Nice, thank you, Pierre. Okay, sub in the coordinate. So I'll just copy it down on the handwritten bit. So we've got y equals a over x plus 3. We have y equals 8, and we had x equals 1. So 8 equals a plus 3. 5 equals a. Nice and easy. So sometimes they'll just ask you to find the value of a, in which case it's fine to leave that as your answer. If it says solve the function, then what you would finally give as your answer there would be y equals 5 over x plus 3. So a bit of a nuance there depending on what's being actually asked. Okay, so that was the first one done live. Question 2 is closer to what we were having a look at. In fact, it's pretty much identical to one of the examples we've done. So rather than, yeah, how are we going to approach question 2?
Can we just sub it in again?
Yeah, so we got 3 pieces of information there. We got asymptote, asymptote, and point. Are you saying start by subbing in the point?
Oh no, you can put the x in h's place.
Yep. So you're going to have your x minus 3. That's good. Where's the y going to go?
In k's position.
Yep, in k's position. Perfect. And to finish it off, yeah. That's good, Charlie. H minus... actually, hang on. H... Yeah. It's a bit tough to say h is minus 3, Charlotte, because they've given x minus h, if you put h as minus 3, that becomes x minus minus 3, so x plus 3. So watching out for exactly what's been written here will allow you to determine what sign h should actually have. That was a DM, I'm not just talking to myself. Okay, so h should be 3 in that case, k should be 4 in this case, and this final point, what are we doing there?
Subbing it in.
Yeah, sub it in. Only thing left to solve for is a, which I've shown you how to do at the beginning. Cool. Okay. Won't necessarily do question 3. This time we got 2 points. We won't do like the actual arithmetic unless you want to see it. What strategy do we need to know how to use if we have 2 points and 2 unknowns?
Do we set up simultaneous equations?
Absolutely. Yeah, set them up. Does anyone want to see me go through those live, or are we happy enough with how that would look?
Can we see it live, please?
Sure can. Okay, so get my calculator out the way. Going to have y equals a over x plus k. And we have 2 points. So the first one is y equals 8x equals 1. That's going to give you a plus k. That's equation 1. And the second one was 7 is y and negative 1 is x. So 7 is the y, negative 1 as the x. There's your equation number 2. All right, we have our options here. We could do elimination, we could do substitution. How are we going to do either? Where should we go from here? Yep, we can do elimination here. So what elimination should we do if this is equation 1 and this is equation 2? Capital A minus little a. I'm not 100% sure what that means. A minus a. So if this is equation 1 and this is equation 2, when you do elimination method, you do elimination based on the thingos. Okay, we can do 1 minus 2. Yeah, so that'll eliminate the k in that case. So you got equation 1 minus equation 2, which means looking vertically and just performing your subtraction. 8 minus 7, a minus minus a is going to give you 2a, and as we saw before, well, from the beginning, the whole point of doing that was to kill the k's, and so we've achieved exactly that. Rearranging for a, not so bad. What do we do once we have our a value?
We can sub it back into the first equation or second equation and then solve k.
Exactly right, yeah. I'm not a fan of negatives, so I would just chuck it into equation 1. As he said, you could go either way with it. Half plus k, 8 minus a half equals k. So 15 on 2 equals k. You can give a decimal if you like. A lot of the times, shouldn't k equal a half? We solved a equals a half. Maybe I've done some math incorrectly.
Because we're minusing the a's, like we're getting rid of the a, so wouldn't k be the remaining one?
If you wanted to give, yeah, so I wasn't sure what you meant by capital A minus A, so I ended up with Gopatap's method, which was do equation 1 minus equation 2. So that would be 8 minus 7 for 1, A minus minus A for 2A, and then K minus K for 0. You could go the other way around and eliminate A. That would be equation 1 plus equation 2. That's perfectly fine to do. It's just not the one that the one that I wrote down here. Is that a bit clearer?
Yeah, thank you.
No worries. Yeah, okay, we got our A, and then we got our K. This one was asking for just A and K, so at the very end, I would say something like A equals a half, K equals 15 on 2. Even though you have them in 2 spots, you have solved them both, it's nice to give your assessors something easy to look at and be like, yep, that's my final answer. Okay, that is that one. Question 4, we basically already did in question 2. Question 5 is a root, but it's still as trivial as 1. Let's see. Question 6. Yeah, okay. We'll have a look at question 6. So you've got some square root with a bunch of unknowns, specifically 2 additional unknowns in there, and it's going through 2 points. What do you think we do in this circumstance?
Once again, simultaneous.
Once again, simultaneous. Yeah. So we submit those points and we rearrange. This one will look slightly different, so it's just going to require you to square to cancel out some of those roots. Okay, so we've got y equals a root x take h. The first point is y equals 2x equals 1. 1 minus h. That's equation 1. And then what y equals 4, x equals 10. Bit weirder here, because now you've got roots involved. How might we solve this?
Two minus one.
Okay, equation 2 minus equation 1, just to show you what that would look like, that would be 4 minus 2 for 2, and then you would have a root 10 minus h minus a root 1 minus h. I don't think that's going to quite do it, because we didn't kill a variable. So minusing isn't quite what we're looking for, unless I'm missing something there. What else could we potentially do?
Would it be 2 divided by 1?
Yeah, that's better, putting a division in there instead. The division will be more effective, because if you imagine just putting, well, he's done 2 divided by 1 instead of 1 divided by 2, but just for the demonstration, if you imagine a division symbol there, divide down will cancel the a's, and then you just sort of simplify this. But we will do 2 divided by 1. So 2 divided by 1, 4 divided by 2 is 2, a divided by a is 1, and then root 10 minus h divided by root 1 minus h. There's only a h involved here, and so the question now becomes, how do we solve this? What should we do on the next step?
Square both sides.
Yeah, squaring now is doable for sure. For those who don't know, if you square a set of brackets, you can distribute that square through the top. If you square a set of fractions, rather, you can distribute that square through top and bottom. So yeah, that is a nice way of going about it. So 2 squared is 4, 10 minus h, and then 1 minus h. And well, from here we're just dealing with a linear. So nothing too crazy. 4, 1 minus h equals 10 minus h. 4 minus 4h minus 10 plus h equals 0. That's going to be 3h over here, and then minus 6 over there. And so we're going to have minus 2 for h. Okay, and then how do we cap it off?
Sub it back into equation 2.
Yep, equation 2 works fine. So h, so we're going to have 4 equals a root 10 minus minus 2. So we're going to have 4 equals a root 12. 4 over root 12 equals a, and then root 12 is 2 root 3. 4 4's a, hang on, 4 3's are 12, yeah, 2 root 3. So you're going to have 4 over 2 root 3, or just 2 over root 3 is equal to a. Anyone need to revise how to simplify surds? So how we went from root 12 to 2 root 3. If not, we can move on to, okay, 7 and 8 you don't have to look at. Question 9. Okay, yeah, question 9 will be a good one. Although it's very dense, so it's hard to do a screen grab of everything. Let's grab at least the top half of that. And we'll do 9a once I put this in the chat. The main thing here is going to be how you translate the graph key information into here. Have a think about that, and how do we do 9a? Maybe a bit tougher.
Can we just do simultaneous again because we're 2 points, which are intercepts?
Going straight for simultaneous is a bit on the tougher side because we've actually got 3 unknowns, A, H, and K, and we're only given 2 points here. So it won't quite work out too well.
Or could we just look at the translations?
Yeah, translations will help to simplify things down a bit. What would that look like?
Since I'm guessing that the 1, -2 has been translated from the origin, we can imply that the K is like -2.
Yep.
And H was 1.
Perfect. So yeah, the thing to notice for not just this one, but everything, is that now you've got to understand exactly how the graphs work and how those can be mirrored up with their key features. We looked at those in the initial little lecture bit, which was you really care about, for square roots, the starting point, or the vertex. For hyperbolas and truncus, it's the asymptotes. They've got a circle in here, but we don't look at circles in methods, at least not explicitly in the study design. But yeah, that is fine. And then, okay, let me just write it out first. Y equals a root x. Well, actually, I'll let someone finish it. So what does the function actually look like after subbing in that vertex? It was a shift right by 1 and down by 2.
Y is equal to a root x minus 1 minus 2.
Yeah, x minus 1 and then minus 2 at the front. Brilliant. For those who may have been unsure, whenever you have a minus on the x, that means a shift right. Whenever you have a plus out the front of the x, it's a shift left. And it's the opposite for the vertical. But okay, we have that now, which means there's only one unknown left over, what do you think we would do to finish this off?
Sub in the point given.
Sub in the point, yeah. Now, we've seen me do that maybe 3 times now, so unless anyone wants me to finish that one off, I think we could probably safely move on. Interrupt me if you need to. But the next one, yeah, we'll do the part B. So, as I said before, we've got some additional information. We have to care about what that would look like in the function there. So what could we immediately start solving regarding the hyperbola? I should specify the part B hyperbola.
We can see that there's been like the h would be 2 because it's been translated to the right. The asymptote has been translated to the right by 2 units.
Yep.
And then k would be also 2 because it's been translated up 2 units.
Exactly right. We've solved for h, we've solved for k. Say it with me. What's the last thing to do to finish off and solve for a? No? We haven't done it to death enough? What do we do with that last piece of information?
You sub in the point to
Sub
the
in the
equation.
point. Yeah. Every single time we've seen this a, you'll see all these graphs are going to have some point that's just sort of floating there, looking like it's not really pulling its weight, but really it's the key to finishing off the entire question. Yeah. You get the key information from most things pretty quickly. Sub in the point, solve the unknown. This one here, part C, is a bit interesting. We won't necessarily do it. It's worth understanding that they might not always label the point that's given to you. Now, that didn't matter a whole lot for this one in particular, because they did give it out here as well. But let's say they only gave like one of these asymptotes. You'd actually have 2 points here to work with. The first being 3, -3, but the second one actually being the origin. Like, usually they're pretty bad at drawing their line through the exact origin, but this time they've actually got it bang on. Like, I've seen weird shit where it's been like out here and just never actually touched the axes at all. But all that to say, essentially, don't necessarily wait for every point to be labeled. If it goes to the origin, it might not label it for you. Okay, barring the circle, is there any more of those kinds of questions we want to do? Just shout out and I'll go back, otherwise we can move on. You've got a screen grab for it as well. Okay, we've got some CAS stuff, we've got, oh, and then just circles. So, just CAS stuff then. Not too sure why this is CAS, to be honest. I guess I don't really trust you to do this tough arithmetic with 10s and 3s, but really it is the same thing as before. You've got some A, you've got some B, 2 points, 2 unknowns, simultaneous. Now, able to do the circle for question 9. I can do the circle. I will say for those who aren't super keen with the circles, it isn't accessible for methods, but I will do it just for fun. On request. Okay, so the way circles work, I'll just copy it down to the handwritten bit. X minus h all squared plus y minus k all squared equals r squared. Okay, so the way circles work, it's a little bit wacky in that this is setting your horizontal translation, this is setting your vertical translation, and both of these are with reference to the center of the circle. And this is your radius right here, the r value specifically. Now, the thing that's a bit wacky about this is this vertical acts like this horizontal does, where if I do y minus 1, that is actually a shift up by 1 this time, and y plus 1 is a shift down this time. So if you look at what's going on in the circle, which I'll draw underneath, okay, we had -5 and -2. Circle, circle, circle. And then the center was that x equals 2, y equals -2. Okay, so first things first, the center point, which is perfectly drawn, is going to be set by your translation terms. So if we're shifting right by 2, that's going to be x minus 2. If we're shifting down by 2, that's going to be y plus 2. Because again, it's a bit backwards with relations. Or at least counter to what you would normally think. And then the r squared bit, the r that you're specifically looking for is the radius in this case. So if we're starting at, if you look horizontally, because that's the only thing you really can do here, the horizontal distance between -5 and +2 is going to be your radius in that circumstance. So that's going to be a radius of 7, and then just to finish off the circle, you go squared. Would you like me to clarify any more of that?
No, that's all good.
Easy. Okay, that is that. Now, on to some CAS stuff. So you don't need the CAS for these questions, but it is nice to at least know how you would have to, well, how you would use the CAS should you be in a tech active environment. So I'll show the TI Inspire first because that's the one I know the best, and I will try to blunder my way through the Casio and see if that works out well. Okay, my recommendation whenever doing any simultaneous on the CAS is to define your function at the beginning before you try to plug it into simultaneous. So for TI Inspire, it's menu, 1 for actions, and then 1 for define. I call all my things h of x just because, well, I know it's just immediately on the left-hand side, and a usually gets taken up. So it's easy to spot on a non-QWERTY keyboard. This always annoys me, the fact that it's not QWERTY. But anyway, and so you can even see it here, right? Like there's A in this thing. You don't want to be doubling up on letters for no reason. H is usually reserved for functions anyway, so it's a nice letter to use. Okay, as for the actual simultaneous, menu, 3 for algebra, solve system of equations, 7, and then 1 for, again, solve system of equations. Pretty sure you can pick this too. I've just never used it. This has been useful for literally everything, so there's no real need not to pick anything else. Click down, relabel your variables. So in this case, we cared about A and B. You don't necessarily have to do that there. You can go in here and change them up if you need to. And then you just submit your points. So in this case, it was 3, 10 as the first point. So that means y equals 10 and x equals 3. And we also had the opposite for the hyperbola. So 3 equals h of 10. Hit enter, and you're sorted there. That's TI Inspire. Now, let's see what I remember about Casio. Well, that's a great start. We're on the wrong screen. Go back to main. Okay, now I believe it's in, whoops, the keyboard. It's one of them, math 3 maybe? Math 2, math 3. Uh-oh. I get the feeling it's one of... Oh, where is it? I won't spend too much time if I can't find it. No, it's just fraction. Maybe I could find it in here. Sim. Oh, actually, it's this, isn't it? Yes, it is. Ha, found it. So it's this button here that you want. But as I said, you want to define things before going into there. So if we just kill that real quick, I think in math 3 there was a define. Yeah, there it is. Same thing as before, call it some function, h of x in this case. We've got a over x minus 2 and plus b. Going back to where we had it. I think it was math 2, wasn't it? Nope, not that one. Oh no, don't tell me I've lost it again. Math 1, okay. These look so similar. The matrix and the simultaneous. But yeah, it's this one that we care about, and if you hit that multiple times, you'll get multiple entries in the simultaneous. But okay, we just do the exact same thing as before. 10 equals h of 3, and then 3 equals h of 10. And all we got to do is put our a and b in here as commas. And that's going to give you the same solution. Just to show you what happens, if I touch this multiple times, you'll see it just adds more simultaneous to the list. Cool. I've saved myself from embarrassment by showing you how to use it on both cases. That's pretty much it, really. There's some circle stuff here, but again, that's not particularly accessible. You'll see they've starred it for that reason. Okay, was there anything left over in that chapter that you guys want to have a look at? Or shall we get on to the chapter summary stuff? While you have a think, I'll just sort of scroll through and see if there's anything special worth looking at here. Question 7's a bit special. Let's have a look at that. So we want to show that this linear touches the hyperbola only at a single point. So I'll write that one down. Okay, x plus 4y equals 4. And we got some other function, just for fun, I'll call this y2 equals 1 over x, just so you can see these are two separate functions. So we want to prove that the linear only touches the hyperbola at a single point. I haven't actually explained exactly how to do this yet, I don't think, anyway. Certainly not for this specific circumstance. Any thoughts on how you might start anyway?
Would we make both the equations equate to each other?
Yeah, precisely. So a couple ways you could do that. You could rearrange this to get y equals mx plus c and then sub them into each other. Or you can skip that and just say, this is already y. I can see a y there. I'll just slide it in directly into it. X plus 4 times 1 over x. So x plus 4 over x equals 4. So yeah, if you see that immediately, just shove it in. Otherwise, feel free to do your rearranging. There's no real difference there. Okay, we've achieved that. It's a great start. It is getting us closer to the answer. Where should we go from here?
Do we bring the 4 over to the left side of the equal sign and then put 1 over x on the right side?
Yeah, why not? X minus 4 equals, now this is 4 over x, but yeah, 4 over x, sure. What else?
Do we bring 1 over x into the equation? Do we introduce it?
So that's what we actually did here. So the reason why we have this at all is because we put this 1 over x into that.
Okay. Then we can just solve now by by multiplying x on the left side.
Yeah. So
and then solving for quadratic.
Yeah, so just solving for x at this point, which is, yeah, effectively solving a quadratic after you multiply everything by x. Yeah. So multiply everything by x. X squared minus 4x equals minus 4. X squared minus 4x plus 4 equals 0. and you've got whatever method you want at this point. You could do factorization, which would be the best way, because it's just -2 and -2. You could do quadratic formula. You could do completing the square and then rearrange that, although, truth be told, that is just the longer way of doing the quadratic formula. So if you solve for x, you'll get one solution here. So let's just finish that up. So x minus 2 is our factor. X equals 2 will be the solution. X equals 2 is not the required answer for this question, though. It does say prove or show that the line only touches at one point. So what is it about this that we could tie up in a nice little statement for our assessors to actually answer the question? What is it about that that shows that we've only touched at one point? Maybe consider the converse. What would it look like if we touched at multiple points? Well, let's just say 2 points for a hypothetical. What would we expect under that circumstance?
We would get like two different like answers from the quadratic.
There you go. Yeah. If you had multiple touch points, you would expect multiple solutions. So one wrap-up statement would be something like one solution ... saying therefore touches once. Just a little thing like that. Like, you might get the mark for this. It isn't what the answer of the question is, though. This answers the question. The rest of this just proves it.
Chris, instead of like factorizing, could we just like use a discriminant and then show if the discriminant equals to 0, like there's only one solution?
Bang on. Absolutely. Yeah. So as soon as you see like 1 point, one solution, anything like that, you can pretty much be pretty certain that a discriminant approach would be possible. So if we had a super crazy thing that would be a lot harder to do by hand, then discriminant will usually simplify that down to something a bit more nicer. So yeah, discriminant, for everyone else, tells you a number of solutions to a quadratic. And so if you have discriminant equals 0, that means only one solution. So just to show out what that would look like, discriminant of this, so discriminant of anything, b squared minus 4ac, where these come from the quadratic. So you want discriminant to be 0. B is -4, so 16 minus 4 times a, which is 1, times c, which is 4. 4 4s are 16. 16 minus 16 is equal to 0. And so you would still use this statement at the end of this, but yes, those are two different ways of proving it. Nicely done. Cool. Okay, whoops. Let's not knock the camera out just yet. What else we got? Question 8. Another fun one. Hyperbola. Points lie on it. The line PQ cuts the y-axis at B and the x-axis at A. Okay. Yeah, why not? This will be interesting, at least to chat about. It's not a typical question, that's for certain. So I'm looking at question 8 for those who haven't caught on to what I was saying. Okay, we have y equals 12 over x. I'm just going to give you guys a visual of what's going on currently. So 12 over x, it's a basic ass hyperbola. It's going to have some points, so we'll call it 2, 6, like that. We'll say -4, -3, so close enough. It's got those points. This one was called P. This one was called Q. So it's worth understanding that when you get a whole jumbled mess of information there, it's good to draw a little picture to see what's going on. Okay, and then the line PQ, so that's connecting these points. Ideally use a ruler. I just somehow don't have a ruler. PQ is going to cut at the y-axis at b, so this thing here is called b, and it's going to cut the x-axis at a. This thing here is called a. So, our goal is to figure out the coordinates of a and b. What might we start doing?
We figure out the equation of the linear
Yeah.
between P and Q.
Yeah, it's almost got nothing to do with hyperbolas, at least not yet. So how do we find the equation of a linear?
First we'd want to do like y2 minus y1 over x2 minus x1 to
Yep.
find the slope.
Sounds good to me. Okay, I'm going to call this number 2. This is going to be called number 1. Okay, so 6 minus 3, so 9. And minus 4, oh, hang on, I've gone backwards. It's 2 minus 4, so 6. Yeah, that checks out. Okay, slope of 3 over 2, achieved. What else we want?
Then you would want to sub like one of the points in to get C, the y-intercept.
Yeah, that's good. So you start with some y equals mx plus c. We know that our m is 3 over 2, so we can put a 3 over 2 for the m, and any point will do at this stage here. The goal is, of course, there, solving for c. 2, 6 looks nicest. So y equals 6, 2, because that cancels that down. You've got 6 equals 3 plus c. C is therefore going to equal 3. A linear only needs an m and a c. So y equals 3 over 2x plus 3 is that equation of the linear. That is this shaded line here. Is that clear to everyone so far? Sing out if I need to clarify that. Okay, but once we have that, where do we go from here?
We just figure out the x and y intercepts of the linear line.
Yeah, precisely. X-intercept, y equals 0, y-intercept, x equals 0, or, for linear it's always just whatever this is your y-intercept. So, reminder that b was the y-intercept, so capital B is going to be 3, and then x-intercept, let y equal 0, going to have 0, 3 over 2x plus 3, minus 3 equals 3 over 2x, divide everything by 3, minus 1 equals half x, minus 2 equals x. And it's also worth just quickly checking to make sure, hey, have I drawn this in a way where those numbers even make sense? Does it make enough sense for 3 to go here? Yeah, it's between the 6 and the 0. Sounds fine to me. And does it make sense for minus 2 to be here? Yeah, not to scale, so it's close enough to where it should be. Okay, and so to give your... I just realized that was off screen. Whoops. So to give final answers, you would say capital B equals 3, and you would say, that was called A, wasn't it? Yeah, A equals minus 2. Again, in a neat little spot for your assessors to see. Okay, so that's part A of that, finding those coordinates. Now we've got to prove that PB is equal to AQ. So, PB, that's a interesting question. So PB is just this segment of the line, so P to B, and AQ is this section of the line. And we're trying to prove that their equations, for what they would be described as, are the same. Weird question, because they all came from the point on this line anyway. So, any thoughts on what you might do just to please the assessor? Because this one is definitely a bit on the weirder side.
Would you find the gradients and the y-intercepts of PB and AQ to prove that they have infinite solutions?
Yeah, that's even a better way of stating it that I would have said, actually, proving infinite solutions between the two. Yeah. So to summarize that, basically, instead of just doing the linear from Q to P, you do the exact same method we've talked about, but for P to B and for A to Q. You're just using different sets of points, and you're proving that those two equations are identical based on that. What a grind to get there. Because if you think about all that effort to get Well, I mean, yeah, I don't know. Lines from here to here. Doing that twice more to get your y equals mx plus c's. But yeah, that's how you would do that. Now, does anyone want to see me repeat this 2 more times, or should we just move on? Okay. All these are starred because we don't have to do them necessarily. Though, this one's weird because semicircles are functions. So you should have to do that. I'll have to get back to you on that. What did they start this for? Have they put a thing? Yeah, I guess maybe they think even semicircles aren't necessarily accessible. I'll briefly touch on it, just in case it does matter, and if anyone's doing it in school, you'll be able to use this. So, the reason why we know this is a semicircle comes from how we handle the root. If you remember the first time, if you were in that class, the first time that I introduced the square root, I mentioned that you only take either the positive or the negative, depending on if there's a plus or a minus sign out the front, even though square roots are typically plus and minus. And that's because it turns it from a relation into a function, if you were to do just a plus or just a minus. It's the same thing here. The reason why I know it's a semicircle is because the thing on the inside isn't just x, it is x squared. Now, if I were to start rearranging this, you might notice the general form. If I square both sides, I'm going to have y squared equals 9 minus x squared. And if I get this x squared over here, I'm going to have x squared plus y squared equals 9, which is 3 squared. So this is the general form of a circle. Normally when you rearrange this, you would have a plus minus, giving you the full circle. It's a semicircle because we cut off one of the halves. If you have a plus, you have this. So this is plus. If you have a minus, you have this. You have the bottom bit. So when we have a graph of this one here, it's the plus, we convert our 9 into 3 squared, telling us we have a radius of 3. There are no translations in there, so you can see there's nothing directly on the x or on the y. So we're going to start at the origin. Radius of 3 means out here, and because it's positive, we give this section. This is also going to cut at 3. You can solve that by x equals 0, or you just know that it has a radius of 3, and so starting at the center should cut at 3. Both of those are fine. It's worth noting, these points here are defined. You don't do open circles there, you do darker spots. I think that's about it. That's all I can really say about that. If you have any translations or so, they will appear here and here. So if you have a look at like 12D on the screen share, this y plus 3 is going to mean a shift down by 3. This x plus 2 is going to mean a shift left by 2. And this is just the radius there. So that's going to be a radius of 2, because that becomes 2 squared. If you didn't fully get that, that's fine. This is supposed to be non-accessible. But I know some people do end up looking at this. Do I need to clarify any of that? Or are we happy with that explanation? This is odd. What's this one? Y equals this, x equals that, y equals... Okay, no, that's nothing. That's just summing in the point. Equations of asymptotes. We've looked at this a lot already. Range. Yeah, we've talked about that already from the beginning. That you don't have to do. Yeah, we could do 8. 8 looks weird, even though it's not actually anything different. So I'll copy it down, just so we don't have to work out of 2 different screens. Yeah, okay. Y minus b equals negative root a minus x. And a and b are both positive values. A greater than 0, b greater than 0. So we care about the endpoint and the y values. We want to know what both of those are going to be. What might we do here? Or maybe even before that, what kind of graph is this? If you were to describe the name of the graph. What should it behave like? If I rearrange it like that, what does that now look like? So we're dealing with the square root here. This will be the typical square root graph that just has one semi-portion of it shooting off either to the top or the bottom, depending on what it is. Like, for example, if I were to plug in some random numbers here, y equals negative 2 minus x plus 3, this should start to look a bit more like what we're seeing here. It's got double reflections. It's got a reflection out here, a reflection in here. Yeah, so this is just the square root graph, the typical thing that goes like that. Now that we understand that, as far as starting point goes, we need to know horizontal and vertical translations when it comes to starting point. So, slightly tricky. What are the translations here?
It's reflected on the x-axis?
Yeah, so it's reflected, for sure. So if we were doing like all the transformations, then yeah, we would label the reflections, we would label the translations. For the starting point, the only thing that actually matters is the translation parts. So what are the factors in there? What letters dictate the translations? So, you know, the up, down, left, right stuff.
X and B?
Close. B is one of them. X isn't. It's actually the A. Even though the X is located there, that doesn't necessarily make it a translation factor. It just means they've did the terms in a different order. Like, for example, if I were to rewrite this again, minus x plus a plus b. I mean, yeah, it doesn't necessarily say x is the variable and y is the name. So technically, they probably should have specified this is a function y of x, but you're supposed to assume y and x are the variables of the function rather than the transformations applied to it. Now, there's an interesting thing that we have to do here to know the true horizontal translation. Either tell me what we have to do to fix this up or what the actual translation would be.
When you say that, would it be like A units up and down and B units left or right?
Yes, that's the kind of thing we're
saying,
looking for. We're looking for up, down, left, right sort of situation. You do have those slightly backwards though. The A should be the horizontal and the B should be the vertical. But yes, that's what we're trying to look for. So to explain this, whenever there's a coefficient on the x, it doesn't matter what that coefficient is, could be a -1, could be a +5. To reveal the true horizontal translation, you have to take that out as a common factor. And that's what that would look like. Y equals negative, bracket, negative, x minus a. Right, you want to take everything off of that. This truly reveals that when you have minus a, you shift right by a. When you have plus b, you shift up by b. Now to give a quick example, because we're about to hit time, if I did have square root of negative x plus 1, this is only defined for where the inside of the square root is greater than 0. So if I have negative x plus 1 greater than or equal to 0, negative x greater than or equal to negative 1, x less than or equal to 1. So it starts at 1, even though you'd expect this to shift left by 1. So that's the reason why I recommend taking a factor out of this, because now it looks like something you're able to tell a bit better. You could just do this for that. You could just chuck this as greater than or equal to 0. It's up to you how you want to go about it. But okay, if we're shifting right by A and up by B, that means our starting point is going to be A, comma, B. And then for our y values, because we've hit time, I'll just kind of go through the rest of this. This negative sign here means it's flipping downwards. And so when we think about all the possible y values, if this is the coordinate AB, then our range is going to be from y equals b all the way down to negative infinity. So the way they've written this out would be, you'd say y is less than or equal to b. It's very rare that you get it to look like that. Usually you would give an inequality, an actual interval, but yeah. So to match that all together, y less than or equal to b, and then a starting point of a comma b, that's going to be answer C in the multi-choice. If anyone wants me to clarify that, feel free to stay behind. Otherwise, I'll let the rest of you enjoy the rest of your day. Take care, guys.